Okay, Chapter 2, the solvent water, solvent for biochemical reactions. In this chapter, we're going to spend some time reviewing the properties of water and polarity, and we'll look at hydrogen bonds, acid, bases, and pH. I'm not going to spend time on titration curves, but we will do a little bit with buffers. And I'm going to try to just do a short bit on water and polarity, maybe hydrogen bonds in this lecture. So as a review from your general chemistry, you should review, if you don't remember, what electronegativity is. This is a unitless number which describes the ability of an element to attract electrons. It has important consequences for the chemical behavior of molecules and atoms within molecules. Just to review on the periodic table, in the very last group, the noble gases, they have zero electronegativity. Electronegativity increases as you go from left to right on the periodic table and as you go from bottom to top. So the most electronegative element on the periodic table is fluorine. That means fluorine has the greatest ability to attract electrons. And the least electronegative element is cesium. And so in general, as you get closer towards fluorine, an atom has the ability to attract more electrons than ones that are further away. So oxygen is more electronegative than carbon. And so if you have a bond between carbon and oxygen, oxygen's ability to attract electrons will pull the density away from carbon, giving it a partial negative charge. And when carbon loses some of its electrons in the sharing, or some of the electron density, not a full electron, it will assume a partially positive charge. So of biochemical importance, oxygen is one of the key atoms we look at, and nitrogen, and we consider both of these to be high on the electronegativity scale. Hydrogen is low, carbon is somewhat intermediate. And so when you have a covalent bond between an atom that is more electronegative than another, you get a polar bond. And that's what I was alluding to in that carbon-oxygen bond. So in the polar bond, electrons are unequally shared, and the atom that is more electronegative will get more than its share of electrons, and it will assume a partial negative charge. And in this case, we have oxygen and we have hydrogen in water. Oxygen is more electronegative than hydrogen, and so it will pull electrons towards it away from the hydrogen for both of those bonds, and so it will get a partial negative, and each hydrogen will have a partial positive. When you have a separation of charge, you have what is known as a dipole moment, and that's represented with these arrows. And the arrows are traditionally drawn with a plus on one side, and that is where the partial positive charge is, and the head of the arrow is where the partial negative charge is. For water, these two dipole moments align along the bond, the OH bond, like this. But in this case, in the vertical axes, the dipole moments cancel, and when they sum, you have one in the horizontal plane on this representation pointing towards the oxygen. Carbon dioxide is a linear molecule, and this is an example of a molecule that has polar bonds, but the molecule itself is nonpolar. So as we said, a carbon-oxygen polar bond is polar, and a double bond between carbon and oxygen will also be polar. But in this case, the dipole will go in along the carbon-oxygen bond, and because we have the same magnitude of polarity in either directions, and they are opposite, those dipoles sum to 0. So anytime a dipole moment sums to 0, you have a nonpolar molecule, even though it contains polar bonds. So some of the solvent properties that we need to look at with water is how it interacts with ion pairs, also known as salt bridges, and ion-dipole interactions. So an ionic bond, and actually don't really like the term bond when we refer to ion pairs, because bond suggests a covalent bond. And in those cases, electrons are shared. In ion pairs, electrons are not shared. But these are interactions where a positive ion and a negative ion are held together by their charges. A salt bridge is a term used more commonly in biochemistry, and it's often referred to charged groups within proteins or DNA or other macromolecules that interact with each other. It's the same thing as an ion pair, but generally referred to more often in a macromolecule, something big. And so this interaction depends on the attraction between oppositely charged species. Ion-dipole interactions are when you have one fully charged species and then something with a partial negative charge. So for example, a carbonyl oxygen. So maybe I have a sodium ion and it's interacting with the partial negative end of a carbonyl. So this is our ion and this is our dipole. So this is called an ion-dipole interaction. It's not as strong as a salt bridge. A salt bridge or an ion pair, in that case, you have two things that are fully charged. Here we have a full charge and one partial charge, so because the magnitude of the charges is not as great, it is a weaker interaction per mole. So this illustrates ion pair interactions here. And when you have a chloride anion interacting with water, that is an ion-dipole interaction. But the Cl- interacting with Na+, this is an ion pair. And these are shown in different forms. Again, potassium with water, chloride. And notice that the potassium, because it's positively charged, is interacting with the negative end of water. The chloride, because it's negatively charged, is going to have an ion-dipole moment with the positive hydrogen, partial positive hydrogen in water. And so you may be asked to draw an ion-dipole interaction between an ionic compound like magnesium chloride and water, and I would expect you to orient the water molecules in such a way that the opposite charges are interacting. Then there are also dipole interactions, and in this case you have two dipoles. There's nothing that's totally charged, but you have two polar compounds. So we have water here, and then this looks like this is an alcohol of some kind. And again, opposites attract, so the partial negative charge on the oxygen in alcohol is going to interact with the partial positive charge in water. And a similar thing can happen with ketones. There are also van der Waals forces. These are non-covalent associations based on weak interactions of transient dipoles for one another. They're called van der Waals interactions. Think about London dispersion forces is an example of van der Waals interactions. Dipole-dipole interactions, these are forces that I just showed on the previous slide that are between two permanent dipoles. Dipole-induced is when you have a permanent dipole and something that is normally nonpolar. And induced dipole interactions, these are London dispersion forces, and these are between two things that are normally completely nonpolar. And what you wind up with is a synchronization of the movement of the electrons, so that you have temporary dipoles that may align in one direction at one moment and then 180 degrees the opposite in another. They are constantly moving. So here's an example of a dipole-induced dipole. Okay, so here is our normally nonpolar species. This happens to be oxygen. And oxygen is nonpolar because it has two bonds shared with the same element, so they have equal electronegativity. And here we have water. And water has permanent dipole. And so when they are close enough together, the partial negative charge on the oxygen may induce a temporary dipole that creates a partial positive in the oxygen molecule. So this is something that's normally nonpolar, but when it is next to something that is polar, the electrons will be repelled by the partial negative on the oxygen in the water to create a partial positive temporary dipole in the oxygen. Induced dipole, this is when you have something that is normally nonpolar. So again, we could have, we could have something like a methyl group, two methyl groups that are in a protein, and we know that carbon and hydrogen, when that's all we have, this is always a nonpolar species, a nonpolar molecule. And so by themselves, they are nonpolar, but when they are close together, and induced dipole, or these are called dispersion forces, or London dispersion forces, they essentially have to be they're so weak that they actually have to be in contact with each other, or very, very close to each other. You get a synchronization in the movement of the electrons that's represented here, such that you have dipoles that may align, right? So this is going to be very, very weak. They have to be very close together. And if we were to look at a snapshot at some later time, you may see that there is a reversal in the dipole because these are constantly fluctuating. So the strength of these interactions is completely dependent on the magnitude of the charge, or very heavily dependent on the magnitude of the charge. So first thing I want to point out is that the strongest quote bonds we have are covalent bonds. So that's what's represented in the top two rows of this table. CH is a covalent bond. OH is a covalent bond. Those are going to be stronger than any of the non-bonding interactions. An ion pair, just for reference, is going to be about 90 kilojoules per mole. Notice that that is still weaker than the covalent bonds between oxygen and hydrogen, and carbon and hydrogen. Okay, so as we get to smaller and smaller charges, so now if we're looking at non-bonding interactions, this is our ion pair. And they actually say it's a little bit weaker than what I've had, but I've heard 90 kilojoules per mole. That is the strongest among the non-bonding, non-covalent bonding interactions, because you have two fully charged species. If you have one ion and something that's not fully charged, a dipole, it drops from about 80 to 20 kilojoules per mole per interaction, so weaker. The hydrogen bond, is a special case of a dipole-dipole interaction, and they are generally about 20 kilojoules per mole. And then van der Waals interactions are much weaker, the dispersion forces, so those are about 4 kilojoules per mole. So as you go from something that is fully charged to something that has no charge, the strength of the interaction drops considerably.